So the other type of special circumstance we're going to look at, we did the vertical circle type thing, is we're going to look at horizontal circles. And again, horizontal circles on something that's non-rigid structure, so it can act a little bit differently. So if you got here, we'll just draw a picture. We got a person, holding something. They're whipping it around a circle. If they're whipping around in a horizontal circle, well, that's just the wrong tool. There we go. If they're whipping around in a horizontal circle, if they're going really, really, really fast, it might look something like this. But you usually have to go in pretty fast. If it's on a rope or something like that, it's not going to make a perfect flat circle like this, because the rope is going to droop down, and instead of making like a flat disc type shape, it's going to make sort of more of a almost like a cone type shape. So let's get rid of this here. Get rid of that. There we go. It's going to, instead of the rope being nice and sideways like this, the rope is going to, of course, droop down because of gravity. Here, we'll even change the color. So something like this, as it is going around in a circle. And of course, it keeps on going around, goes behind. But the rope is going to droop down. It's not going to be a perfect flat circle, so you get more of a cone type shape out of it. So that's the other kind of special circumstance we're going to look at. Is instead of vertical, we're looking at horizontal circles, again, on a non-rigid structure. And of course, the big difference here is the rope or the chain or whatever it is, blah, blah, blah. Basically, it sags down, okay? And when it does this, it'll actually it's going to make an angle. So, I'll get rid of this, get a little more clear space here. Get rid of that right there. Basically, we get an angle going on here, like this, with the horizontal. There's our angle right there. I'll draw the mass or the mass at the end, whatever it is. Okay, so we get this angle going on, and it sort of traces out like a cone type shape. Now, there's a couple of similarities, a couple of differences to other stuff that you guys have done, but let's just start by mapping out the forces. If I map out the forces, gravity is the easiest one. I've got the good old force of gravity is going to go down. What you feel along the rope, of course, that would be tension. So, of course, tension you'd feel along the rope. And then, well, where's the FC? Well, FC actually always, of course, points to the center of the circle. And, of course, the center of the circle is not where his hand is. This is no longer the center of the circle. The center of the circle is actually down here somewhere. So the FC actually points over there. And we can actually take this FG and move this FG over here. Change that to transparent. There we go. We can move that FG over there. And I prefer it over there because you can sort of see the triangle that is actually being created as this thing is going around. So basically FG and FC sort of make a triangle with the angle in there, and the tension is what you would feel along the hypotenuse. Now, since FG and FC are always perpendicular to each other, so here FG and FC are always perpendicular, now we have a constant tension. When we do the vertical stuff, the tension would actually vary depending on location. Here, they're always perpendicular to each other. So we have constant forces, constant tension, so that's a little bit easier. But there is one other slight change that we have, and that has to do with the radius. The radius is no longer along the actual rope itself. The radius is down here. It's that distance over here. So probably one of the key differences between this one and other stuff that you guys done, probably the key diff, is the radius is no longer equal to the length of the rope or the chain or whatever it is you happen to be using. So that's one of the key diffs between this and the previous ones you've done. Now the thing is, the radius and the length, so that'll be like the length of the rope, they share the exact same angle as the forces. So you got the forces create the angle, and then those radius and length measurements actually share that angle for the situation. So once you have one angle, you've got the other angle, which actually makes it relatively easy to go back and forth. Just don't mix the forces and the lengths together. And just basic trig. I mean, radius is just the bottom of the triangle, so it's no big deal. It's just be the radius is going to be the length times the cos of the angle. So, you know, you got the two forces making the angle is shared by the distances, the radius and the length, but you got a nice constant tension, so you don't have to worry about that at all. It's relatively straightforward, okay? Just the angle is just a little bit different, but that's not too bad to work with, okay? So let's just throw some stuff in here and see what we can do and solve for a few different things, okay? So let's just take may as well just use the person that's right here, no big deal. Suppose they are whipping around a mass, and let's say we've got, let's say the rope is, I should change color, no, it's okay. Let's say the rope is 1.8 meter long rope, and let's say this is a 0.65 kilogram mass. Let's find out how fast it's actually going to do this. Okay, no big deal. We can sort of piece things together, and you know, we have the angle too. Let's say this is a 25-degree angle. Okay, so let's just find a few things, piece a few things together, and map things out. I'm just going to redraw it a little bit here so I can clean things up a little bit. So I've got my rope like this. I've got my mass right there. Okay, so 1.8 meters. This is 25 degrees, and this is 0.65 kilograms. Okay, so I'm just going to start by finding some basic stuff. And I got the mass. I may as well find the force of gravity. That's really straightforward. So if I find my force of gravity for my whatever it is going around, I got the 0.65 times the 9.81, so pretty easy. And I got about 6.4 newtons. So you could put that over there if you want to. I like to just make it part of the triangle itself, and I know that is 6.4 newtons right there. So I have a right triangle. I got the 25 degrees. FC is at the bottom of the triangle. I know my FC is down here. So if I use tan theta, I can relatively easily figure out what FC has to be, right? Because tan 25 is going to be your FG divided by your FC. So if I just look at that, tan theta is going to be my FG divided by my FC. I've got my FG, I've got my tan theta. I can solve for FC relatively easily. So solve that, and my FC is around 13.7 newtons, which looks about right given the general diagram of proportions. So 13.7 newtons at the bottom. Okay. So I'm looking for the speed of the object. So if I want the speed, I need my FC is equal to mv squared over r. Well, I've got the mass, I've got the FC, and v is what I'm looking for. Actual radius, I'm just missing the radius. So that's not too bad because I know the length and I know the angle. So of course radius would be the L cos theta. So it's not going to be the 1.8. It's going to be a little bit shorter, not a whole lot shorter, but a little bit shorter. And that's like 1.63 meters. And I can take that and put that into there. And then I've got my M, I've got my FC, I've got my R, I've got everything I need to solve for my V. So I'll put my values, I'll rearrange that. So it'll be FCR divided by M, don't forget to square root. And then I can calculate my speed. And I get about 5.9 meters per second, and that's it. Okay, so that's basically it. So again, it's nothing really new, just a slightly different application, slightly different setup. Get the angle incorporated, which to tie the two forces together, as well as tie the length and the radius of the path together. And that's pretty much it. And that's the same ideas as what we've had before.